Hi and welcome to this second part of creating a 2D flocking algorithm in Unity. So far we've created a flock which flocks to a goal position which is in the center of our unit manager, and that's this square you can see in the scene, and its goal location for the flock is the center of that. So if we move it around, the flock will adjust its position. Now we're going to add in a few other behaviours which keeps the flock, if they're within a certain distance of each other, together as a unit, and so they will therefore be heading towards the centre of their flock, as well as trying to keep in alignment of the direction that they're travelling. Right, so what we're going to do for that is, first of all, we need a distance. Now that will be set up in our all units. So this is the code that is on the unit manager, and we're just up the top going to add in this. So we're setting a range slider between 0 and 200 that will show up in the inspector for this public int neighbor distance equals 50. So this is basically going to tell each unit in the flock that if another unit is within a distance of 50, then they are considered your neighbor, and they're the ones that you should care about joining with and staying aligned with. Anybody outside of that range is not your neighbor and is not your concern, basically. So if you're like 100 units away from another group, then you'll just ignore what that group is doing. Right, so that's in the all units. So just save that. Now, if you haven't seen this used before, this allows you to set a range for the values of the next variable that's coming after it, and it also gives you a little slider in the inspector. So I'll just show you that. Go to the unit manager, and you'll see that the neighbor distance has now come up here. It's set to 50 by default, but you can use this slider to change it, as well as the range if you want to change the range in the code. Next, we go into the unit code, so the code that's on each of the individual units. Let me just change the size of this window for you. And in here, we will add our two functions, one for aligning with our current group and one for cohesion, so staying with our current group. So align is to move in the same direction as the group, and cohesion is to stick with the group. So there's two different functions occurring there, although they look very similar. So let me just add them in here above the flock function, and I'll go up and show you the first one. The first one is align, which is this one here. So it gets hold of the distance of the furthest neighbor. So this is the value that we just set in the unit manager before. Anybody outside of this range we ignore. Okay, then we set up this sum vector2 value and zero it, and also a count, because what we're going to do is add up a bunch of vector2s and then divide it by the count, which is how we find an average. And we're finding that average in this case of the alignment, or the direction that things are traveling in, and the direction that each unit is traveling in is stored in its velocity value, and you'll see that in a moment. So first of all, we set up this for loop to loop around all of the units that are in that units array for our manager. Okay, so we're only concerned with units that belong to our unit manager, because I said in the previous video that you could have as many unit managers as you liked with different types of units. Okay, so this will sort of keep everybody of the same type together. And then, because we're looping around all of these units, we will pick up our own ourself. So this will pick up any time that we've found ourself in that list, and just ignore it, because we don't want to add our own alignment and that into this. Okay, the next thing is we work out the distance between the location of this particular unit and another unit, or the current other unit that we've looped to get out of the array. Now, if that distance is outside of our neighbor distance, then we don't do anything. But if it's inside the neighbor distance, so if D if the distance to this particular other unit is less than our maximum neighbour distance, we sum up the velocity of that unit. So this just loops around and adds up all the velocities together. And as it's doing that, it's counting how many velocities we've added. Now, after that loop has finished executing, we then say if the count of the number of velocities that we added together is greater than 0, then we're going to find the average. So we're going to divide the sum by its count. And then we calculate this steer value. And the steer value is going to be this average heading of the group minus our current velocity. And then return that value, which will be used in the flock algorithm later. Now, if there was no neighbours, then we're going to just return a 0 vector. So it won't have any effect on our velocity at all within the flocking algorithm. So that's the align, which sums up the velocity value. The next one is cohesion. Now, it looks exactly the same as the previous one. We're getting the neighbour, we're creating a sum, we're initializing a count, and then we're looping around everything. But the difference is that we're not summing velocities. We're summing, in here, the location. So this time we're getting the average position of the group rather than the average direction of the group. And calculating, again, down the bottom here, the average. And then we're not returning that average, but we're doing a seek on that average. And remember from the first video is that the seek gets you the vector towards a goal location, and it's used to find the goal location. But in this case, our goal location is the average location of the group, and so we're going to return that. Again, if we've got no neighbours, then we're just going to return 0, so there's no effect on the particular unit. With these two new functions, we need to integrate those into the flock function down here. So our flock function is going to be replaced. So let's just highlight all this code and I'll put the new code in for you, and then I will go through and explain how it's changed. So the flock code now has our location and our velocity set up as before. But now I've got an if statement in here saying if random.range between 0 and 50 is less than 1. So this kind of gives us like 1 in 50 chances every time this flock code runs to recalculate our alignment and cohesion and goals. If we take this out, then you don't get such sort of fluid movement because every update loop, the unit will calculate its new flocked position. Now, that's pretty heavy processor-wise to do that every unit, doing it every update loop. So by doing it like having a 1 in 50 chance that you will do it, it just gives it a little bit more fluidity so that a unit will keep sort of moving in the directions it's moving until it's told to then calculate through here. You can try changing this and see what you get, or get rid of that if statement and how slow it makes things run. First thing inside this if statement is a new variable called ally, which is getting the align returned value, and then co, which is for cohesion, getting the cohesion returned value. So this is grabbing hold of those values, the average values that we worked out. Then we're also doing our goal seek that we did before. Now when we calculate the current force, we're actually going to add our goal location plus the alignment value plus the cohesion value together. So now that they're all mixed in together, and will determine what our current velocity, or I guess force that will apply to our velocity, will be added to. And then of course we're normalizing it to set it back to a length of 1 and then applying that. Okay, so just save it and switch back to Unity and press play. Now, you're probably not going to notice too much of a difference, but there is a lot of difference going on here. They're no longer just interested in getting to the goal location. Okay, so there is a goal location, but you can see things like, look at this guy out here, he's become a bit separated from his neighbors. And the outskirts of this becomes a little bit more fluid. And each time you run it, because of that randomness, you will get a different effect happening. And the group is not so rounded as it was before as well. And it's also swaying further away from the goal pos. And you can see that just around the edges, you get just a little bit more behavior. Now, of course, with that goal pos in there, you're not going to see really advanced behaviors happening in this particular group. So there's a little bit of interesting stuff going on in there. The other thing is, if this keeps going back and forward, as you can see, units are starting to get flung away from the group because the velocity hasn't got a maximum velocity or a maximum force to be applied. So this can just keep slingshotting around here and get further and further away. And you'll start to sort of lose members of the group, as you can see here, that they're now flying past. And you might want this to happen, but I'm going to now show you how to just limit this from getting out of control. And for that, we need to add in a maximum velocity and a maximum force. Okay, so let's open up the all units code, and at the top of there, underneath our neighbor distance, we'll add in 2 more values, one for max force and one for max velocity. And in this case, I've got a range from 0 to 2 for the max force, though you could ramp this up as much as you like. And initially it's going to be 0.5, and a maximum velocity as well, which is between 0 and 5 with a current version of 2. So save that there, and then when you switch back to Unity and click on the Unit Manager, you will see that you've now got some more sliders that you can use. Those 2 new values will be applied inside our unit function, the code that's attached to each particle. And they will come into play in the apply force function. So find your apply force function, and we're going to replace what's already in there with some new code. Okay, so here it is here. Now the code that was in there before is still there. There's just new code added. First of all, we're setting the force that's going to be applied according to the force value that's being passed through from the flock function. We're then going to assess this force. First of all, we're going to look at the magnitude of the force, so how strong that force is. If that force is greater than the maximum force that we set in the manager, then we're going to normalize the force. And remember, normalizing it is to set it to a length of 1. Once we've normalized it, we're then multiplying the force by the max force, which will make it the length of max force. So what this is doing is capping that force at max force, but because it's a vector, we want it to still be pointing in the same direction. Now, we then add the force to the rigid body as we were doing before, and the velocity will also be set in the same way or restricted in the same way. So after we've added the force, then we're going to grab the velocity's magnitude, and if the velocity is greater than the maximum velocity, then we'll do the same thing with it. We will normalize it, which is this line here, and then we will actually set it to the maximum velocity. And that's how we do it. We normalize it, then we multiply it by it, and that will set it to that. And then at the bottom, again, we have the draw ray function, just so that you can see it in debug. All right, so that's the apply force now. If we save that and we switch back to Unity and have a run of it, you'll find that you're not going to get the slingshot. And if you have a look here, you can see immediately that the vector lengths of the debug draw, they're much shorter, whereas previously they were quite long, the ones that were being generated here. Okay, so we still got some interesting behavior going on, and the group is still sort of meandering, but it's not going to get out of control because it cannot go past those maximum values that you've set for it. To add a little variety, first of all, let's go into our all units, which is our unit manager code, and then just underneath the range, I'm going to paste in some Boolean values, and they'll allow us to turn different features on and off. The first one I've got is seek goal. If this is turned off, then the units will forget about the center of this unit being their goal position, and that'll allow them to wander off wherever they please. Then we've got an obedient true or false. Now, obedience will mean that they will follow the flocking rules. And then we have a willful one as well, which will allow a unit to be how can we say, willful, as in the fact that it will choose to go off in another direction regardless of the flocking rules. Okay, so those values will be used back in our other code. So save that and open up the units code. So in here. Okay, so we'll apply these values down in the flocking algorithm. So the new flocking looks like this. The same velocity and location as we had before. We still have that if statement for random range for the 1 in 50 chance of applying the flocking algorithm, but this time we're adding in our Boolean value for obedient. So if we're obedient and it's 1 in 50 chance, then we will apply the flocking. So if we're not obedient, none of the flocking that we were doing before is going to get applied. Okay, so that's enclosed for that Boolean. The next one was the willful, and the willful one is down the bottom here in this little section. So we're saying that if we're willful and we get a 1 in 50 chance, then we're going to select a new random direction to wander off in. Okay, so that's those values there. And then the one for seeking the goal, you might have noticed, is back up here inside of the obedient function. If we're seeking the goal, then we do the same calculation for our goal location that we did before with the seek function for the center of our unit manager. If we're not seeking the goal, then we're going to determine the current force based on our neighbors, which is our alignment and our cohesion. And so now if you run it and change those values in the unit manager, you'll see completely different behaviors. So let's save that, switch back to Unity, and press play. So while you're testing, if you select the unit manager, you'll be able to play around with these values here as it's actually running. So if we press play, and you see them created inside the box, and they're currently seeking the goal. If you turn off the goal seeking, they will continue on trying to flock but without the goal. Now currently, as you can see, all of their velocities are basically centered into the middle of the group, which is fine because they're flocking with the entire group. So their neighbours are all within 50 distance of each other, and they're slowly drifting off down that way. Now if I turn goal seek back on, you'll see the velocities are all recalculated and they come back to that central position. Now what's quite interesting, if I turn willful on and turn off goal seek and obedient, is that they eventually choose that they're going to go off a completely different direction. This will start to spin, because I've seen it before, and they're going to fly off. Now at this point you can make them obedient, in which case they will go into a flocking behaviour, and they'll start to group together with what they consider to be their neighbours. In this case, the neighbour distance is 50, so that's quite far away. Let me just bring them back into the centre. We'll turn willful off and we'll go back to seeking the centre, and we'll turn this neighbour distance right down to, like, say 2 or 1, and then we will turn off our seek and obedient. We will do the willful for a bit to get them all mixed up so that they fly off, and then we'll go to obedient, and you can watch them start to cluster. So this is them in their flocking behaviour, and if we zoom out on this screen, you can actually see where they've gone into their little groups, and they'll stay in their little groups and continue on those directions until something else changes. So that change might be that you've selected seek goal again, and we can watch them in this scene views that they've all turned around. They'll stay within their groups because we've got the obedient ticked, and they'll all head back into that center position that you'll see here. So we've got some quite interesting behavior. Now what's really nice with this is if we duplicate our unit manager, so we've got 2 unit managers, and then we'll just move this one across a bit, and that one's still over there. We'll move back the other way, and we will duplicate the green prefab, so Control D on that, and let's call this blue prefab. And then select it, and over in the inspector you want to change its sprite from the green one to something else. So I've got this blue one called purple, which makes sense, doesn't it? So we've changed that to purple so that the unit manager duplicate, instead of using the green prefab, we will set it to use the blue prefab. Okay, so let's run and see how we go. Okay, so now they're all mixed up, but remember the blues are going to go over to this goal location that's on this side, and the greens will go over to that side. But because you've got the nice physics in there as well, you're going to have some quite interesting interactions and behaviors. Like you can see this green guy here, he's actually got stuck with the blues and swept up with the blues. And so therefore you might turn off the seeking. And you can also play around with the maximum velocity as well, and just have a little bit of fun with it. If you'd like to request a tutorial, or if you'd like to see some extra content that's exclusive only for my Patreon subscribers, please go to patreon.com/holistic3D. I've also got a Udemy course that you can go and have a look at that goes through all of the basics of the mechanism system in Unity. And let's not forget my book that's coming out soon, which is the 2nd edition of Holistic Game Development with Unity, which you can pre-order on Amazon now. And that's it for this tutorial. I hope you learned a few things and enjoyed watching. I'll talk to you next time.